to introduce the second law of thermodynamics. And for instance, let's remember that the first law of thermodynamics will state that the energy can be transferred from one place into another. For instance, if we have a high temperature source, and for instance, I have a lower temperature source, the heat will start to flow, right? And the heat is not destroyed, or the energy is not destroyed. It is nor created. It will be conserved. But the second law will state the direction of this transfer. You might actually understand now that the heat is going to be transferred from the high temperature source to the lower temperature reservoir, let's say. And this is very natural. What fixes this direction is the second law. The second law will limit the performance of any system. It is very easy to turn work into heat, but then to turn heat into work, that is not that easy. What do? We use a thermal machine. A thermal machine is a machine that is going to be working in such a way that we have, for instance, a source of heat, high temperature heat, and it's going to enter, for instance, a cycle. And for instance, we will need a heat exchanger, a boiler, for instance, that will have a fluid of work. We usually use in this case steam, okay? So we're going to input heat so that the steam is going, for instance, to go into an overheated steam, and we're going to use that, for instance, in a turbine in order to produce work. Then we're going to use, for instance, a condenser in order to get rid of the heat that is remaining, and then, for instance, we use a pump, right, to start all over again the cycle. We need a little bit of work, and this is a thermal machine. Its purpose is only to produce useful energy from heat. That's it. The only thing that we need to do is to get rid of lower temperature heat. We define then what we call the efficiency. The efficiency is going to be equal to the output over the input, what we want over what we want. What we want over what we have to input to the system. What we want here, we want work, useful work. What do we have to input? We have to input high temperature heat. An energy balance of the work might actually tell us that this is, for instance, the higher temperature heat minus the lower temperature heat over the higher temperature heat. And for instance, the efficiency is always less than 1. This is something that happens due to the second law. We cannot turn, it is impossible to turn all the heat into work. We have to have, for instance, a remnant heat in the turbine, and we're going to get rid of that in the condenser. This is the Kelvin-Planck statement. It states that it is impossible for any device that operates in a cycle to receive heat from a single reservoir and produce a net amount of work. Or, in other words, you cannot turn all the heat into useful work. It is impossible. If you use the same cycle but you invert it, for instance, you have an evaporator, you are getting, for instance, lower temperature heat from there. Then, for instance, you have refrigerant here, and what you have, for instance, is a compressor. You have to input some work, and then you compress the refrigerant. While you have compressed the refrigerant, you have, for instance, a condenser. And in this condenser, you are going to get rid of heat. At the very end, you will input, for instance, the refrigerant into a throttling valve, and then you close the cycle. In this kind of inverse cycle, you might actually want to produce this heat from work. This is, for instance, a heater. Or you might want, for instance, to get rid of heat. That could be, for instance, a refrigerator. Instead of analyzing, for instance, the efficiency, well, you need, for instance, to analyze the cup. You can have a cup for a refrigerator. What is the cup for the refrigerator? It's the amount of heat that is lower temperature heat over the amount of work that you have to input to the system. And for instance, you might actually state this equation like this. You can also have a cup for the heater. What you want from the heater? You want the high temperature heat, and you have to input some work. So for instance, this will be the expression at the very end. So it is very important to understand that instead of having the efficiency in this case, you have a cup. The cup, for instance, is usually higher than 1, but it has a limit. Clausius' statement of the second law will state that it is impossible to build a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. So Clausius' statement will actually limit the coefficient of performance. COP states for coefficient of performance. And there is another concept in thermodynamics, for instance, that are called the perpetual motion machines. These are machines that are actually not existing, that might violate first law. For instance, they produce energy from nowhere. They can also violate second law, stating that, for instance, you are going to produce all the energy or all the heat, you are going to turn it into work, right? So in this video, we were stating, for instance, the second law of thermodynamics. We reviewed what is, for instance, a thermal machine in order to turn heat into work, what is the concept of efficiency, the Kelvin-Planck statement of the second law, the inverse cycle that might actually work for heaters or for fridge, what is the coefficient of performance, what is the Clausius statement, and finally, what is the perpetual motion machine.